Hi, everybody. So I wanted to give you a quick revision of recursion and then give you a quick exercise to do when this is over. Um, so I'm not sure how good the quality of this recording is going to be, so excuse me for the poor quality. So really quickly, just remember recursion is when a method is called continuously or multiple times, but the most important thing is there was some sort of a base case which halts the recursive call. So I'm going to quickly go over all these slides. I'm uploading them so you can go back and look at it if you need to, but I'm going to go back over this Fibonacci problem that we did in class. But I changed the slides a little bit, so I wanted to go over it with you. So here we have the n numbers, and here at the bottom we have the n factorials. Here's a solution. I don't want to read it out for you. You can pause it and read it if you'd like. You don't have to start with the base case. So line 2 in my case talks about the base case. You don't have to start with the base case. It's just how I like to write code, only because it keeps it clear in my mind. Like this part will always tell me when the recursive call should stop. Moving on, what I would really like to do is walk through step by step this recursive method, just to give you an understanding of how this should work. So if you look at this really quickly and we use the number 4 as an example, you'd have to make some sort of a function called. So my function is called factorial. I'm calling it factorial, and I'm giving it a call 4. And now if I go into this, what I'd have to do is, well, let's see how this would work. So when I call factorial 4, this method is run, and it will return n multiplied by factorial of n minus 1. That essentially means 4 multiplied by factorial 4 minus 1. So this part here is calling the method again. 4 minus 1 is 3, so that's the same as calling 4 multiplied by factorial 3. So you can just ignore that first part. Now, factorial 3 is going to call this function again, but now I have a new value for n. My new value for n in this case is 3. So I'm going to now say 3 multiplied by factorial of 3 minus 1, which is 3 factorial 2. Moving on, 2 factorial 2. When I reach this 1, when I call factorial 1, it calls lines 2 and 3 of this algorithm. And this returns an absolute value instead of calling the function again. So this is my base case. And I've reached my base case at this point. And what that is telling me is, well, at this point I have an absolute value, and I can fill in values for this line and this line and this line. So let's see how that would look, right? Let's see what that would look like. So if I know this is n equals 1, I can replace factorial 1 with the number 1. That changes that line to 2 multiplied by 1 now, and that's equal to 2. And I can replace factorial 2 with this value, which is now going to be 3 multiplied by 2, and now I have a value here, 6, and I can replace factorial 3 with the value 6, which is going to be 4 multiplied by 6, and now I have a final answer for my problem for factorial 24, right? Now, yeah, you may say that, well, the iterative approach to solving this problem is simpler, and you are absolutely correct. It is simpler, but this is not always the case. So as we're going to discuss in later slides, this is not always the case that an iterative approach is simpler. So I'm gonna skip this problem. You should have already done this problem. Make sure you have it. There's a solution here for you. You can go back and look at the slides if you want. And I want to quickly talk about linear search. So we started doing linear search in class. You should have had a chance to do both the iterative approach and the recursive approach for linear search. I'm not gonna go over the definition of linear search. You can go back and look through it on your own time. But what I am going to do is I am going to start talking about binary search today. So I talked about this at the very end of class. So I want to talk about this in a little bit more detail today. So binary search is a search algorithm which can find an element. That element can be called X or N, whatever you like, through a sorted list, right? Through any sorted array. Note, the array must be sorted. So they must be in order, right? So I have the algorithm here for you, but instead of going through here, what I want to do is I want to show you how this would work using an example. So what you have is, assume you have this sorted list. So let's say you have this sorted list 2, 5, 8, 12, 16, 23, 38, 56, 72, and 91. And let's assume you're searching for the element 23. Notice this is a sorted list. Everything is in order. It's in ascending order. It could be in descending order. It doesn't matter. That's still a sorted array. You know, just going through an array backwards to forwards or forwards to backwards doesn't really make a big difference. But notice what you do here is you set a value for your leftmost value. You set a pointer here at your leftmost value. You set a pointer here at your rightmost value. And you set a pointer in the midpoint. All right? So what you're going to do is you always check the midpoint for your search element. In this case, my leftmost value is 2, my rightmost value is 91, and my midpoint is 4. Right? What I'm going to do then, in that case, I'm going to compare. Well, my search term is 23. Is 23 greater than 16, or is 23 smaller than 16? In other words, is the number 23, my search element, greater than my midpoint, or is it smaller than my midpoint? Well, in this specific case, it's greater than my midpoint. And what that allows me to do is it allows me to eliminate all the elements before my midpoint. So the number 2, 5, 8, 12, and 16, I will eliminate all those elements and I will only look at the right side of my list at this point. If the number was smaller than 16, then I would eliminate the right side of my list and I would only look at the left side. So since I have now eliminated all these values, notice my leftmost number now becomes the element of my midpoint, or 1 greater than my midpoint. My right element stays the same, and my middle element changes. Okay, now my middle element, my left element is 23, my right element is 91, and my middle element is 56. So I'm going to do the same thing again. I'm going to say, well, is my search element 23 smaller or greater than the number 56? In this case, it's smaller. So what I do is I eliminate the entire right side of my list. Okay? So now I have a left element, a right element, and a midpoint. In scenarios like this is not always going to be the case, but in this specific scenario, it seems like my left element and my midpoint is the same element. It's fine if you just do the numbers. So for example, you know, greatest minus smallest divided by 2, and then you round that number up. Sometimes this will happen. You should already know the rounding algorithm. So in that sense, we found my element, 23. And I've only checked for the element 3 times. So there is an argument to be made for efficiency here. If I was doing sequential search, I would search element 0, element 1, element 2, element 3, element 4, element 5, and I would stop. So I would have searched 5 different elements before I found my desired element. In this case, I've only searched 3 times and I found my desired element. So that should show you, well, there is an efficiency argument to be made here. Now, because this is an example and we're only working with 10 elements, it might not show you how efficient, how much more efficient this is significantly. So I do want you to think about that. So let's quickly go ahead and look at the next slide, and I'm going to give you something to do. Okay, so I want to talk about the binary versus the sequential search algorithms. Linear search or sequential search is useful when data is unsorted. If the data is unsorted, there is no accurate way to find a specific desired element, right? You have to go through every single element to find the answer. And that has to be the case. If you can think of a better way to do it, you're going to be very, very, very rich. Unfortunately, it just doesn't exist, right? So it's the only way, really. It's the only sure shot way of saying, okay, we've looked for this element and we haven't found it. All right, but it's very slow because you have to go through every single element in your list. Binary search is a significantly better algorithm in terms of its performance, as it eliminates half the data set in each iteration. So if you start with a data set of 10, you'll eliminate 5 in the first iteration, right? The next iteration, you'll eliminate another 2.5. In the next iteration, you'll eliminate the last one, right? But But it only works when you have a sorted list. If you have an unsorted list, you have to go back to binary search. And that's why we need to know both these algorithms. So what I want you to do is I want you to write an implementation for the binary search algorithm in Java. Use REPL. I do not want you to think about the iterative approach at all. Use recursion, only recursion. My tip to you is start with the base case. When does the recursive calls stop? And then build your algorithm from there. Along with your implementation, I want you to write some comments in your code discussing the following. So just read this. I'm just reading this part out word by word at this point. If you had a list of 100,000 sorted elements, compare and contrast the efficiency of the sequential and binary search algorithms. So these are sorted lists, yeah? I want you to consider the best case scenario and the worst case scenario for each algorithm. Now, what is the best case? The best case is what is the shortest number of iterations for me to find my element? What is the worst case? What is the largest number of iterations for me to find my element, right? So as an example, if you were doing a sequential search and the element that you were searching for was the very first element, element number 0, then sequential search would be faster than binary search, right? Because you'd find it immediately after you started searching. But if you had a 100,000 element long list and you're using sequential search and your element was somewhere at the end, so let's say it was element 999, yeah, then you'd have to go through 999 other elements before you found your desired element. So that makes it a problem. So the best case scenario and the worst case scenario is kind of an informal discussion of efficiency, right? This is something that I want you to think about. If you'd like, you can come up with an array and find numbers for it and kind of just, work through that. Don't forget, when you're writing your algorithm, you also must write a case for when the algorithm does not find the element you're looking for. That's really important. If you'd like, when you're implementing your binary search algorithm, you can go ahead and use this data set. Obviously, there's a little problem here. I will fix this before I send it to you. But yeah, that's it. So I want you to work on this. Along with this, there's going to be a part on Google Classroom, which asks you to submit everything that you've worked on in class before we head off for this long holiday. I hope you're all being safe. Be clean. Don't go out. Don't party. Do some AP Computer Science. Once you're done with this, we're going to be working on some progress checks because we're coming to the end of the AP contents. So let's do the progress checks for this, but stay tuned for that. Another video coming shortly.